All right, let's begin.
I won't say anything. I won't say shit.
So we're going to continue with series convergence tests. I had your test to give back, but I'll give those back at the end because I don't want to be distracted while we're going through these series convergence tests. So we spoke about telescoping series. We spoke about test for divergence. We spoke about geometric series. We spoke about the integral test. And last time we introduced the P-series test. And that's what we're going to continue with now. We had a few examples. A couple we've seen before. I just want you to look at them in a different light, I guess. Those two guys, C. Okay, so A. So what can you tell me about this guy? Alright, so we can think of this as a P-series where P equals 1, which tells us
That it converges.
it diverges. The series diverges. So, remember the P-series test said, because the P-series test, it looked at things that look like 1 over n to the P specifically, and goes from 1 to infinity, and we know that it converges if and only if P is larger than 1. In other words, it diverges if your P is less than or equal to 1. Yeah, so this actually diverges, and again, remember, this is a very famous example. This is the harmonic series. So, the series of 1 over n actually has a name. It's called a harmonic series. Very important and very common divergent series example because it's one of the simplest examples we can think of a series that diverges, yet the limit of its expression approaches 0. Right? So that's called the harmonic series. One way you can think about the harmonic series is you can think of it as a P-series with P equals 1. In B, you could say here it's a P-series with P equals 2. And this, nothing else to say here. This means the series converges. That's all there is to it. What about C?
C is also P-series or P is 1/2. So diverges.
You can say which is a divergent P-series. So eventually it gets to the point where even pointing out the p-value is just such a silly thing to do that we just say, it's a divergent p-series. You all know what that means. It means the p is larger than 1, less than or equal to 1. And what about D? Converges or diverges?
Converges.
How do you know?
It's the same as 1 over n to the 11 over 10, which is greater. 11 over 10 is greater than 1.
11 over 10 is greater than 1, so it's a convergent P-series. P is 11/10, which is larger than 1. So that converges, this diverges, this converges. This was that guy that was equal to pi squared over 6, which of all things. This guy diverges. Now, the P series, of course, as you can tell, it's a very specific situation, and of course, it's going to be easy to actually see that that's the situation. So, of course, you're never going to actually be asked a problem like this, right? Because it's kind of, there's nothing to test you on, really, at the end of the day. The P series, these guys really come in, they're really useful. In comparison. So next we're going to talk about some comparison theorems. So these are some other ways that we can talk about series converging. And again, the two that I'm going to tell you about, again, comes from our intuition from improper integrals. And with the integral test, we kind of know this thing to be true. We'll cover two comparison theorems. Inspired by the integral test and the comparison theorems for improper integrals. So here is the first comparison test, which we often just refer to it as the comparison test. For emphasis, people might say the direct comparison test, but people usually leave off the direct part. So this is, I want to say 6, or is it 5? Is it 6?
I think it's 5.
It's 5. 5, the direct comparison test. Now, when you look at the statement of this test, and if you know the comparison test for improper integrals, you're going to see that this is an analogous statement right off the bat. So suppose you have two sequences that they're both non-negative, and you know one is bigger than the other in this fashion, then you take the series of each of those guys, it maintains the inequality, and 1. If the series of Bn converges, so does the series of An. And if the series of An diverges, so does Bn. No conclusion can be made in other cases. So again, reminds you, or should remind you a lot about that comparison theorem for improper integrals. Basically, you have two guys that are always positive, which means, worst case scenario, they're going to diverge off to infinity, because you're just going to keep adding stuff, and it's just going to blow up eventually, because you're just adding positive or / non-negative numbers. Now, if you're adding up a bunch of things and the guy on the far right adds up to a fixed number and he stops adding up, then the guy over here has to also stop adding up. So if this guy converges, he stops at a real number, it forces this guy to stop at a real number because he has to be somewhere between 0 and that real number. Similarly, if the middle guy diverges off to infinity, then the larger guy must also diverge off to infinity because he's always bigger than or equal to that guy. So that makes a lot of sense. You won't know otherwise. So if your upper series diverges, you can't make any conclusion about this series. And if this series converges, you can't make any conclusion about this series, because the other one could both diverge or converge without making the inequality false. But in those two specific instances, you can actually make a conclusion. Now, let's do an example for you to see how this is applied. Now, later on, I'm going to mix some examples together of when you would use different tests. So, in the meantime, I'm just going to give 1 or 2 examples per test so you can just kind of see how they would be applied. So, example. Suppose you are given the series, just to switch it up, k equals 1 to infinity. So that's your series. You want to know, does that guy converge or does that guy diverge, right? Might not know what the exact answer is going to be, but is there a meaningful answer is the question. How do you actually go about figuring that out? Ideas, what do you think? What do you try?
Replace 3k with 1.
Huh?
Replace 3k.
With 1?
Yeah.
Why would you do that?
You make it smaller.
And what would you obtain by doing that?
Then check it out like the 1.
So you get 1 over this thing?
Yeah. This converge or diverge.
And then what would that give you? Something bigger or smaller?
Something smaller.
So you'd get something small. If you replace that by 1, you would get something smaller, right? You'd get something over here, right? That looks like the series of 1 over the blah, blah, blah. Okay, then what would you say?
Oh, I had a bad idea. Like take the square root sign away. Make it bigger.
Okay, so taking the square root sign away is going to make it bigger.
Or make it smaller. Make it smaller.
It's also going to make it smaller, yeah. So you want to do that instead of making the 3, 1?
Yeah.
So 3k over 2k to the 5th plus 2k plus 1. Okay, and now what would you say?
I have no idea.
Okay. What does your intuition tell you about this guy? Would this guy converge or diverge?
Converge.
Converge. Why? What's your intuition there?
As it goes to infinity, the lower one just increases more rapidly than the numerator.
Yeah, we go to 0. The last term.
Okay, so going to 0 should not be a part of your intuition when it comes to series. The fact that this thing goes to 0 tells you nothing at all. It does for sequences. For series, it doesn't matter. Right? So if you have so I don't want you to have that as an intuition for series. So if you have the series of an with the limit of an approaching 0, then it tells you nothing. This guy could converge or diverge. So for a series, this idea gives you no information whatsoever, no info. In general, just knowing that goes to 0 doesn't tell you anything, right? Something going. What tells you something is if it does not go to 0. That's the important thing. So there is a test for divergence. If your limit of an is not 0, then you know for sure that the series diverges. But the limit approaching 0 tells you nothing at all. Nothing. Nada. Right? Because if you look at 1 over n, that guy, 1 over n approaches 0 as n approaches infinity. That guy diverges. Look at this guy, 1 over n squared. That guy approaches 0 as n approaches infinity. That guy converges. Right? So here your an approaches 0, here your an approaches 0, but they both have different behavior. This one converges, while this one diverges. Going to 0 tells you nothing. That's the first thing, very important. So that should not be a part of your intuition. The fact that the limit is going to 0, completely irrelevant for series. But going by what was said earlier, when you're going off to infinity, it is true that your intuition should be based on the bigger guys. Now, essentially, what you'd want to do is you'd want to compare this, for example, to a series that looks like 3k over 2k to the fifth, which you, of course, would realize that's 3 over 2, because we can factor constants out of series, of 1 over k to the fourth. Now, what would you be able to say about this series?
Oh, it's a P series.
Converges.
It's a convergent P-series. Now, by comparison, you can say that this converges, but what would you be able to say now about that guy?
Nothing.
Nothing. Why can we not say anything?
Because it's smaller than the original.
The only time converges tell you anything is when the bigger guy converges. So, you looking at this, finding a smaller guy that converges, tells you nothing, right? So that's another thing. If you have the intuition that this thing is going to converge, how would you get the intuition? Well, the same way that we got the intuition here. You look at that and you have to make a little guess. Is it going to converge or is it going to diverge? And you need to know if this guess is going to pan out. What I would do is, since we're going off to infinity, I realize that the biggest guy in the top and the bottom, they're the ones who are going to control the game. At infinity, k compared to k to the fifth, not even close. That guy might as well not exist. So you essentially kind of ignore them. So what I would essentially want to do is I would want to compare to the series with 3k over the square root of 2k to the fifth. Right? So I look at that, that's going to be my first thought. What's going on as we go off to infinity? The little guys don't matter. This guy's going to behave like I'm adding this expression over and over. So now, what would that expression look like? Write that in a nicer form, a form that's useful to us.
Take a 3 over square root 2 outside the series.
Mm-hmm.
1 over
1 over
k to the 3.
3 over 2. What? K to
1
3
over
over
k
2.
to
This is like a 1 over k to the
3 over 2.
3 over 2.
that converges.
Right, because this is k to the 5 over 2, and then we're going to subtract 1. So it's 1 minus 5 over 2, so that you get minus 3 over 2. So that's the guy. Now, this guy, you know, is a convergent P-series. Now, the hope is, since I know that's convergent, now the question is he bigger than that?
Yeah.
Yes. How do I know it's bigger than that?
Because you're adding like the 2k and the 1.
The denominator is smaller.
Because the denominator is smaller. I just took a fraction and I made the denominator smaller. Whenever we do that, we get a larger fraction. So you see this and I'm asking, does this guy converge? Your intuition is going to tell you, ignore the little guys, look at the big guys. Okay, the big guys behave like this. Now, I know that converges. Is he actually bigger than that? Then you're going to notice, oh, I made the denominator smaller to get that, so it is bigger. So now you're going to start writing out, note, 0 is less than or equal to which is less than or equal to 3 over radical 2, 1 over k to the 3 over 2. Since smaller denominator. Okay, so now you kind of have this inequality set up, which mimics the inequality set up in your comparison theorem. And then you can say, since the series of 1 over k to the 3 over 2 is a convergent P-series, the original series converges by comparison. Right? And that would be how you would answer that. So this guy does converge. converges how? By comparison with a p-series. So this is where a p-series comes in handy, right? You're not going to be given a p-series, but chances are, a lot of the times the thing you're looking at, if you ignore all the guys that really don't matter, you're left over with a p-series at the end of the day. That's going to be very quick for you to tell whether it converges or diverges, and then most of your work now is trying to figure out, is this guy I'm looking at bigger or smaller than the guy I have? Now, the hope is you can either find something bigger that converges or something smaller that diverges. Otherwise, you're out of luck. But in this case, the nicest guy to compare it to was a larger guy that converged, so that allows us to take advantage of the first bullet point in the comparison theorem, and I can conclude this guy, I don't know what it converges to, but I know it converges. So that's how you'd apply the comparison theorem. You have some complicated looking series, but you have some other simpler series that you can compare it to. And of course there are going to be, as your intuition from improper integrals and from like squeeze theorem back in Calc 1 kind of tell you, well, I can create something bigger by making the denominator smaller, or I can create something bigger by making the numerator bigger, or I can create something bigger by bounding a sine function above by 1, or a cosine function above by 1. I can make something smaller by bounding a secant function below by 0, etc. Or a secant squared function. So all these little things come into play when you're trying to figure out, okay, that series is kind of complicated, can I compare it to something, right? And the comparison theorem would come into play. And a p-series, these guys are very useful because it's very often that you'd be able to compare something to a p-series. So this is where the p-series actually really shine. Now, there is an important question. There are times when, what if you don't know who's bigger or smaller? If an is smaller than or equal to this bn that you made up, or the bn is actually smaller than or equal to the an. Sometimes the optimal guy to compare things to is a guy that you've made changes that both makes it bigger and smaller, and you're not sure if it's actually bigger or smaller. So if you're not sure the way the inequalities are going to turn, what do? That leads you to the sixth test. This is called the limit comparison test. Now, we don't usually leave out the word limit here. If someone uses this test, they say it, the limit comparison test. Right? So they might say by comparison, and you're talking about the direct comparison test. If they say by limit comparison, they're talking about this. They'll always mention the word limit. And as the name suggests, we actually use a limit in this test. Here is the test. Suppose your an and your bn are positive numbers, and we take the limit, of course as n approaches infinity, of an divided by bn equals L. Okay? So you have two sequences, you divide them, and you take the limit as you approach infinity, and the answer is L. Then, if L is a positive real number, then what you'll be able to say is that the series of an and the series of bn both do the same thing, in the sense that they'll either both converge or both will diverge. And of course the idea is you will know what one of them is doing, right? So if I know for a fact, for example, that bn diverges, it would also mean that an diverges. Or if I know for a fact that bn converges, it would also mean that an converges, provided that this limit gives me a positive real number answer. This is called the limit comparison test. Now, I want you to recognize, in terms of an and bn, knowing who's bigger or smaller doesn't actually matter. I don't actually need to know how this inequality lines up, whether it should be the other way around. It's just take the ratio, find the limit, and a positive real number answer tells you that both the series will actually behave the same. Essentially what this means is like, one is like a constant times the other, right? If you were to multiply both sides by bn here, you realize that an is behaving like some constant times bn. So, let's do an example here. So, we have the series n goes from 3 to infinity of n plus 1 over n squared plus 2 n plus 3. So you see something like that. See something like that. Where should your intuition lead you? Well, of course, you're going off to infinity, so your eyes are automatically going to gravitate towards the biggest guys around, these guys here. So you're going to notice, would like to compare to well, the series of 1 over n, of course, right? So if I just ignore all the smaller guys, the bigger guys are n over n squared, which simplifies to 1 over n. So that's the guy I would like to compare it to. So I look at this and that's the first thing I'm going to think, because of course technically the first thing you want to think is the test for divergence, but the limit goes to 0, so that's not going to pan out. Next thing I'm going to look at, what are the biggest guys doing? Okay, so overall I expect this series to behave somewhat like 1 over n, and I would like to compare it to that. Now here's the issue. If I have n plus 1 over n squared plus 2n plus 3, and I change this to n over n squared, which is equal to 1 over n, I want you to notice what changes we've made, right? Notice we made denominator smaller, right? So that leads to a larger fraction. We also made the numerator larger. Now that leads to numerator smaller. We made the numerator smaller, so that leads to a smaller fraction. Now it's not as straightforward as you might think. If you both change the numerator and denominator, and even if you change them by the same amount, or you change one by a larger bit than the other, it's not always clear what the overall fraction is going to do. To get this to compare to something I'd like to compare it to, I would make two competing changes. One makes things bigger, one makes things smaller. And which one actually carries more weight to it, you know what I mean? That's kind of going to be like, I made a change where I made things bigger and then I made things smaller. I don't really know who actually wins. Does the larger amount that I made it larger by outweigh the smaller amount that I made it smaller by? It's not really clear. So in terms of the 1 over n and comparing that to the n plus 1 over n squared plus 2n plus 3, you don't know if it's this or that, right? You don't know, right? Now, if you're in that situation, if the thing you like to compare it to is something that you're not sure what side of the inequality it would be on, and for the direct comparison test, that's super important. What you can do instead is the limit comparison test, right? So, well, you probably wouldn't write this out. So we're not sure about the inequality. So, limit comparison test. So, in your mind, when you want to know, when should I be using the limit comparison test? It's pretty much in any scenario where you'd want to use the regular comparison test, but you don't know how the inequality works out. Then you just jump for the limit comparison test. So, what are we going to do? So, take an equals n plus 1 over n squared plus 2n plus 3, and bn equals 1 over n, then what is the limit of an divided by bn?
It's 1.
It's actually actually 1, right? Ratio of the leading coefficients. Right? 1 is a real number that's greater than 0. So, conclusion, the series of AN and series of BN do the same thing. And this means the original series that I cared about was the series for AN. So the series of AN, what is your conclusion here?
It diverges.
Diverges. How do I know it diverges? Because the series of Bn is the harmonic series, and I know that diverges. The limit comparison tests tell me they're going to do the same thing. So if this one diverges, that one's also going to diverge. And you would say by limit comparison. So that series is actually going to diverge. It's going to add up to infinity. That's the limit comparison test. So you're pretty much, that guy is useful when the direct comparison test is probably what you would like to do, but you're not sure how the inequalities should pan out.
So if the limit of an over bn is not a positive real number, then
No conclusion. So you'd have to try something else, right? We're going to do a bunch of tests, so you'll have multiple options here. Let's look at another one. Now, of course, at the end, I'm going to, again, kind of summarize all the tests that we went through and when you might want to pick one over the other. The alternating series test is the next one that we want to do. So test number 7. This is called the alternating series test. So, definition, what is an alternating series? An alternating series is one of the form minus 1 to the n a_n, where a_n's are always positive, i.e. signs alternate every term. So if you see a series like, it goes a1 minus a2 plus a3 minus a4 plus a5 minus a6, or you have like minus a1 plus a2 minus a3 plus a4, etc. Things that have this kind of behavior, these are called alternating series. So they alternate between positive and negative numbers. So it's adding and subtracting, adding and subtracting, adding and subtracting, going all the way out to infinity, right? So now sometimes all the guys that you're adding and subtracting, the additions and the subtractions kind of balance each other out so that they stop at some number. Sometimes the additions part overwhelm the subtraction part, goes off to infinity. Sometimes the subtraction part overwhelms the addition part, goes off to negative infinity. And sometimes they fight forever in an eternal limbo, just bouncing up and down between positive and negative and never actually getting anywhere. So all sorts of things can happen with an alternating series, but the pattern of the alternating signs is what should tell you. And it's very common to actually express that with this term here. So that's an important term. So that term or anything similar, so sometimes you might want to put like an n plus 1 to get the sign to start at the step that you want or something like that. But essentially you have minus 1 raised to a power, and that indicates an alternating series, alternate signs. Now, these guys, we can deal with them in a particularly different way. So the test is the following. So given the series minus 1 to the n times a_n, you're going to check certain things. If a_n is positive, an is decreasing. And remember what that means. It means the derivative is negative, or an plus 1 is less than an, less than or equal to an for every n. And at the same time, the limit approaches 0. Right? So a limit being 0 actually does have some significance for this particular kind of series, provided these other two bullet points are occurring. So if all three things happen, then the series converges. And of course, if this one doesn't work out, then it's automatically divergent by the test for divergence. So that's probably one that you would check first. So if you notice that the limit is not 0, then it automatically diverges. But if the limit is 0, and in addition to that, it's alternating signs all the time, and an is decreasing, then it actually is a convergent series, at least in the conditional sense. And why is it important that this is positive? Well, it's because you don't want a negative number to coincide with a negative sign, and so you lose the alternating sign relationship, because that's actually important for this test to actually work out. But that's the alternating series test. Right. So given an alternating series, if these three things work out, the series converges. Example. I have one silly example here, but I have others. This guy. This is the alternating harmonic series. Now the harmonic series itself diverges. This is like the harmonic series, but the signs alternate. So this is like minus 1 plus a half, minus a third, plus a fourth, minus a fifth, plus a sixth, etc. Does that actually converge would be the question. So you'll notice here, this series is minus 1 to the n of 1 over n. So if an equals 1 over n, you can note an is always positive for all n. An is decreasing. And the limit of an equals 0. Therefore, we conclude that this series converges by the alternating series test. That should be it. That's it. The alternating harmonic series converges. Of course, to go by a previous definition, we would say that this guy converges conditionally, because of course we know if we were to put absolute values around each term, we get the original harmonic series, which diverges. It's the alternating series test. So that one's nothing too crazy here, so let's move on. The ratio test is interesting. I want to say this is 7 or 8. I'm losing count. Whatever, doesn't matter.
It's 8.
Now here, this guy can be used with any series. So whether it's alternating or not, whatever behavior it has, you can actually use this test. But there are cases where it's especially useful. It's especially useful if an involves factorials and or exponentials, right? Right, so if I'm seeing like a series like n plus 1 over n cubed minus 4, I'm going to use a comparison test, compare that to 1 over n squared. If I have like 2 to the n over n factorial minus 4, that's kind of a ratio test kind of thing, right? So the moment you start to see these differences, like, oh, there are a bunch of factorials and exponentials around, as opposed to going to like a comparison, I might gravitate towards like a ratio test. They're very useful in this scenario. And why they're useful is because how it's actually applied actually helps you to kill the factorial. I'm going to show you exactly how it would kill a factorial. So, you're given a series, an. Well, there's one condition that you have to have on an. It can't, none of the terms can be 0. But other than that, nothing. Where an is not equal to 0 for any n. Why? Because there's going to be a division. Set up L to be this limit. It's the limit as n approaches infinity of in absolute value. You're going to put an plus 1 divided by an. Right? So again, you're going to kind of take a ratio and take a limit of that ratio. You're going to do it in absolute values though. Right? So L is going to be that number. Here are conclusions you can make. Ooh. If that number is less than 1, the series converges. More than converges, it converges absolutely, in fact. So this series is very nice when you're, especially when you're dealing with absolute convergence. Two. If your L is larger than 1, the series diverges. So this can tell you both about convergence and divergence. Right? So you find this limit. If it's less than 1, it actually converges. If it's greater than 1, it will diverge. If L equals 1, then no conclusion can be made from this test. The thing may converge or diverge if the limit is actually 1 specifically. It's worth mentioning, this is usually not mentioned, but I'll just tell you now. When it comes to rational functions, this test is useless because you'll actually always get the limit being 1. So just a side note, a Jhevon side note. This test is useless if an is a rational function. So if it's a ratio of polynomials, don't even worry about it. It's much better to actually do a comparison test on those guys. Just look who's the bigger guys controlling the thing. If you can't know if that's bigger or smaller than the original series, do a limit comparison test. If you realize it's bigger or smaller than the original series, do a direct comparison test. Yeah, let's but this guy, L will equal 1 for the harmonic series, for the alternating harmonic series, for 1 over n squared, any irrational functions, because you're actually just taking a ratio. The coefficients are going to be the same, they're going to cancel out. You'll always get 1. So, examples. I'll give you 2 examples here. Series n goes from 1 to infinity of minus 1 to the n of n over 2 to the n. N goes from 1 to infinity to minus 1 to the n of n factorial over e to the n. Try those for next time, because we're out of time. Try to apply this test and talk about what these guys are going to do. That being said, let me give you guys back your test and get up here. So try those for Friday.